I think we are live. So, welcome back, guys, again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, my dear students, quickly in the chats, let me know if all of you can hear me, if I'm perfectly audible and visible to everyone. Quickly, let me know in the chats. Every one of you. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Welcome back, guys. Welcome back. Welcome back. Welcome back to one more amazing session from the NEET Conquer batch with me, your chemistry educator, Wassim Bhat. So, what exactly we are going to discuss in the today's session? Let me just give you the quick overview of the things. My dear students, we have started the chapter mole concept and the first session of the mole concept. In the first session of the mole concept, we completed till stoichiometry, right? So almost, I can say some 50 to 60% of the chapter is completed. The remaining chapter, the remaining mole concept, part 2, we are going to discuss in the today's session. Okay? Perfect. Are you guys ready for it? Quickly in the chats. Quickly in the chats, guys. Everyone. Call up all your friends here. Call up all your friends. Let's start the session. Call up all your friends quickly. Let's start the session. Ready for it? Are you all ready for it? Hello, Muhammad Yahya. Hello, Gayatri. Hello, Sandhya, Prince, Anusha, Killer Science, Gotham, Zenith, Aruna. Welcome back, guys. Welcome back. I'll let you know where you'll get the PDFs also. Just wait. I'll let you know. I'll let you know. Someone is asking like when the syllabus will get completed. The syllabus will get completed in 6 months for sure. Okay? 6 months it's going to take. The plan which I have already given you, I'm just following that plan only. Nothing new. Right? So guys, so first of all, the ones who have not subscribed to the channel yet, I would want every one of you to subscribe to the channel right now so that you remain notified about all the sessions which we take here on Unacademy NEET English channel. Okay? So do like the session. Do share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025. This particular session is for everyone. And at the same time, again, I'm saying, if you are not subscribed to this particular channel now or yet, I would want every one of you to subscribe to the channel right now. Okay? Perfect. So already, guys, already, this chapter, I'm not going to give you any break. 4 hours I'll take to complete this chapter, okay? 4 hours sharp will take to complete this chapter. No break in between. Are you ready for that? Are you ready for that? Hello, Sahil. Sahil Malik. That's great. That's great, Srivatsan. It's better if you watch this right now. Yeah? Perfect, perfect, perfect. Okay, one more announcement. The NEET Energized batch, you guys can still enroll in it at 40% off. Currently, there is 40% off going on in the NEET Energized batch, and that batch you are just getting less than 9,000 at this particular point of time. So the ones who have not enrolled yet, do get enrolled right now and start watching the live sessions from tomorrow on the Unacademy platform. Okay? Perfect. All right, guys. So let's get going then. Let's get started with the mole concept part 2. Okay? Just give me a second. My dear students, if you remember, in the last session, we discussed about stoichiometry. In the stoichiometry, I showed you exactly 3 methods. One was the mole method, one was the mass method, one was the volume method, right? Mole method we discussed in detail, and right now I'm going to discuss mass method with you first of all, right? I'll show you exactly one more way of solving the questions in stoichiometry. I'm going to show you one more way of solving the questions in stoichiometry, my dear students, with the help of mass method. Okay? And after that, you decide whatever method you find easy, you apply that method in the questions. Okay? Perfect. So let's get going. Let's get going. Let's get going. Just a second. I hope voice, everything is all perfect. Yeah? I hope voice and everything is all perfect. All right, people. So let's have a look on a question. Let's have a look on a question. If you remember, this question we have already solved in the last session with the help of mole method, right? Now the same question we are going to solve with the help of one more method. And at the end, it's going to be your choice to select the method and follow that. Okay? Now guys, have a look. The question is, calculate the mass of oxygen gas produced. Calculate the mass of oxygen gas produced on heating 12.25 grams of KClO3 at STP. Okay, this is the question. We have solved the same question with the help of mole method. Now, let's have a look how mass method is utilized to solve this question. So we are going to talk about the mass method now. Mass method. My dear students, whenever you use mole method or mass method in stoichiometry, the first thing always is to balance the reaction. This has to be always your first step. Just balance the reaction, right? Now, particularly in mass method, after balancing the reaction, convert the given quantity into mass. Convert the given quantity into mass. If you remember, in mole method, what we were supposed to do? In mole method, we were supposed to convert the given quantity into moles. But here, we are supposed to convert the given quantity into mass. Look at the question carefully and see what is our given quantity. My dear students, we are given with 12.25 grams of KClO3. We are given with 12.25 grams of KClO3. So this 12.25 grams, it is our given quantity. And it's already given in terms of mass only, right? Grams is the unit. It's already given in terms of mass. So no need to change it. It's already given in terms of mass. Okay? Now, I hope every one of you would remember the reaction. We know when KClO3 is heated, it gets converted into KCl, and with KCl, you get O2 as well. Let's try to balance the reaction. This has to be 2 times. This has to be 2 times. This has to be 3 times. Okay? The one whose data is to be calculated. The one whose data is to be calculated. And the one whose data is given. Just relate the two. Just relate the two, guys. Simple and basic. Understand properly what I'm going to say. Understand properly. We are supposed to calculate the mass of oxygen gas produced on heating 12.25 grams of KClO3. So as per the question, we have to heat up 12.25 grams of KClO3. And on heating 12.25 grams of KClO3, we have to calculate the mass of oxygen gas produced. Okay? So I'm going to relate these two things. One thing if I ask you, what is the molar mass of KClO3? Molar mass of KClO3 is 122.5 grams. That means mass of 1 mole of KClO3, that is 122.5 grams. But right now if I ask you, do I have 1 mole of KClO3 here or 2 moles? I have 2 moles of KClO3. If the mass of 1 mole of KClO3 is 122.5 grams, so what has to be the mass of 2 moles of KClO3? It has to be 245 grams. So I'll write 245 grams of KClO3 upon heating gives. Now tell me, what is the molar mass of O2? Molar mass of O2 is 32 grams. That means mass of 1 mole of O2 is 32 grams. But do I have 1 mole of O2 or 3 moles of O2? I have 3 moles of O2. Now you tell me, if the mass of 1 mole of O2 is 32 grams, what has to be the mass of 3 moles of O2? It has to be 96 grams of O2. Right? So my dear students, just look at this particular statement carefully. Whose data I was supposed to calculate? I was supposed to calculate the data for O2. As I told you in the last session, the one whose data has to be calculated, that has to be on the right side. So O2 is already on right side. Done? Look at this particular statement carefully. The statement is written in terms of mass. The statement is written in terms of mass. So which method I'm using here? I'm using the mass method. I'm using the mass method. Now guys, you're almost done. Stoichiometry is telling me that 245 grams of KClO3 upon heating gives 96 grams of O2. Now we use the unitary method. Can I say 1 gram of KClO3 upon heating should give me 96 divided by 245 grams of O2? This is something which stoichiometry tells me, that on heating 1 gram of KClO3, you'll get these many grams of O2. But as per the question, am I supposed to heat 1 gram of KClO3? No, I'm supposed to heat 12.25 grams of KClO3. Now you tell me, upon heating 12.25 grams of KClO3, how much mass of O2 will be produced? 96 divided by 245 multiplied by 12.25 grams of O2. When you solve this particular term, my dear students, you'll get it exactly 4.8 grams of O2. So what did you calculate basically? What is this particular term? This is basically that mass of O2 which is produced upon heating 12.25 grams of KClO3. As simple as that. The same answer you got with the help of mole method as well, if you remember. Same answer. Now it's completely your choice to select the method. Whether you want to approach the question with the help of mole method or you want to approach the question with the help of mass method, the choice is all yours. Okay, let's try to solve one more question, which we have already done in the last session. But right now, we are going to solve the question with one more approach. That is the mass method approach. Do you remember this question we did in the last session? Now let's solve the same question with the help of mass method as well. Let's solve the same question with the help of mass method as well. The first step is to balance the reaction. Second step, convert the given quantity into mass. That's what we need to do. Okay. Now guys, let's have a look on the reaction first of all. It is 3 times NO2 gas plus H2O liquid. It gives 2 times HNO3 aqueous plus NO gas. The reaction is already given in the balanced format. The reaction is already given in the balanced format. Okay. Now guys, look at the given quantity. The given quantity is already as per mass, right? It is already given in terms of mass only. It's 25.2 grams. My given quantity is already in mass, in the form of mass. So I do not need to convert it. It's already in the form of mass, right? No need of conversion. Now look at the question. How many grams of NO2? How many grams of NO2 are required to produce 25.2 grams of HNO3? So as per the question, we need to produce 25.2 grams of HNO3. And in order to produce 25.2 grams of HNO3, how many grams of NO2 are needed? How many grams of NO2 are required to produce 25.2 grams of HNO3? Now look at the question carefully. My dear students, I'm using which method? I'm using mass method. So I have to write this statement in terms of mass. And how exactly? Have a look. If I ask you, what is the molar mass of NO2? 14 plus 32 comes out to be 46, right? So I would say 46 grams, that is the molar mass of NO2. 46 grams is the mass of 1 mole of NO2. But do I have 1 mole of NO2 or 3 moles? Or 3 moles of NO2. Now, if the mass of 1 mole of NO2 is 46 grams, what will be the mass of 3 moles of NO2? It will be 138 grams. So I'll write 138 grams of NO2 here. Okay. Now talk about this HNO3. What is the molar mass of HNO3? Calculate it. It will be 63 grams. 63 grams is the mass of 1 mole of HNO3. But do I have 1 mole or 2 moles? I have 2 moles of HNO3. If the mass of 1 mole of HNO3 is 63 grams, the mass of 2 moles of HNO3 has to be 126 grams of HNO3. Now guys, read the question carefully. Read the question and tell me whose data I'm supposed to calculate. Am I supposed to calculate the data for NO2 or am I supposed to calculate the data for HNO3? Look at the question. How many grams of NO2? How many grams of NO2 are required? So I need to calculate the data for NO2. And the one whose data is to be calculated, that has to be on the right side of the statement. That has to be on the right side of the statement. So what do I need to do? I just need to reverse the statement so that NO2 comes on the right side. So I'll be writing something like this. I'll write 126 grams of HNO3. 126 grams of HNO3 are produced. As per stoichiometry, 126 grams of HNO3 are produced from 138 grams of NO2. Okay? Guys, today you are going to see some mind-blowing questions, right? Just wait for that. 126 grams of HNO3 are produced from 138 grams of NO2. Use the unitary method. Can I say 1 gram of HNO3 is produced from 138 divided by 126 grams of NO2? Right? So 1 gram of HNO3 is produced from these many grams of NO2. But am I supposed to produce 1 gram of HNO3? No. I'm supposed to produce 25.2 grams of HNO3. So 25.2 grams of HNO3 will be produced from 138 divided by 126 multiplied by 25.2. And this will be grams of NO2. Value comes out to be, I think this value comes out to be 27.6 grams of NO2. Okay? So what did I calculate? Check it out. Check it out. What did I calculate? This is the mass of NO2. This is the mass of NO2 which is required to produce 25.2 grams of HNO3. Let me know once quickly in the chats. Can you solve the questions with the help of this particular approach as well? Can you solve the questions with the mass method as well from now onwards quickly in the chats? Quickly, guys, quickly. Jayashri, you have to increase the volume. I cannot do that. I'm already talking in high pitch. Perfect. Done. Wonderful. So I'm assuming that you guys can easily solve these sort of questions from now onwards. Okay. Now, guys, mass method is though done, right? Now, let's talk about, first of all, one more important concept that's called as limiting reagent. Have you heard of this term, limiting reagent? The most important type, the most important concept from the chapter mole concept, because this concept is almost involved everywhere in the physical chemistry. It is almost involved everywhere in the physical chemistry, people. Limiting reagent. So let's have a look what limiting reagent is all about. This is the most important concept of the chapter. Okay. So first of all, how do we define the limiting reagent? I would say that reactant which gets completely consumed. That reactant which gets completely consumed earlier in the reaction. That's something which you call as limiting reagent. The other reactant is called as excessive reagent. Let's get to know about these two terms, these two statements which I mentioned over here. Have a look, people. This is important. Okay. Just to make you understand. Let's say I've got a reaction in this format. A plus B, it gives C plus D. Let's assume it's one balanced chemical equation. Let's assume that it's a balanced chemical equation. Yeah? Let's assume that it's a balanced chemical equation. For example, I'm writing something. At time t is equal to 0. T is equal to 0 means the reaction has not started yet. Reaction has not started yet. What does that mean? That means the reactants have not reacted yet to form the products. Okay? So at time t is equal to 0, reaction has not started yet. So reactants have not reacted yet to form the products. I'm assuming initially at time t is equal to 0, I have got some 10 moles of A and 5 moles of B. Let's say initially I've got 10 moles of A and 5 moles of B. So this has to be 0, this has to be 0 because the reaction has not started yet. Now, my dear students, when the reaction will start, when this particular reaction will start, when the reactants will start reacting, when the reactants will start reacting to form products, what will happen to the moles of the reactants? Initially, I had 10 moles of A. I had 5 moles of B. When the reaction will start, what's going to happen? What's going to happen? Can I say number of moles of reactants will keep on decreasing with time? And number of moles of products will keep on increasing with time? Yeah? Right? So number of moles of reactants will keep on decreasing with time. Can I say there will be a time when one of the reactant will get completely consumed in the reaction? Yes. When the reaction will start, number of moles of reactants will keep on decreasing. There will be a time when one of the reactant will get completely consumed in the reaction. And if one of the reactant gets consumed in the reaction will stop. The reaction will stop. So let's assume B is the reactant which is getting completely consumed in the reaction. Okay? So after some time, you'll find some 0 moles of B left in the container. You'll find that B is completely consumed. B is completely consumed. And you know, that reactant which gets completely consumed earlier in the reaction, what do we call that as? We call that as the limiting reagent. So in this reaction, B has to be what? B has to be limiting reagent. Right? B has to be limiting reagent. If B is the limiting reagent, I would call this A as the excess reagent. I would call this A as the excess reagent. Okay? What does that mean? That means I took initially 10 moles of A, but it's the excess reagent. It's not getting completely consumed in the reaction. So when the reaction stops, there will be some moles of A left in the container. There will be some moles of C which would have formed. There will be some moles of D which would have got formed. Only B is the one which has been consumed completely. Okay? So I hope you just got the idea of what is limiting reagent. In short, limiting reagent is the one which gets completely consumed in the course of reaction. Okay? And when one of the reactant gets consumed, what happens? Reaction stops. Reaction stops. Okay? If one is the limiting reagent, other one is called as the excess reagent. There will be some moles of excess reagent left in the container. And there will be some moles of products which would have got formed at the time of limiting reagent. Okay? I hope the concept is a bit clear to you. Now, we are going to see how this concept is used in the questions. And where to apply this concept, how to apply this concept. That's important here. Okay? So let's try to understand how to apply this particular concept. Let's try to understand. Have a look, guys. Let's try to understand how this particular concept is applied and used. Okay. Let's say I'm writing the reaction as one simple reaction, N2 plus H2. It gives NH3. This is the reaction, very simple and basic reaction. Okay. Now, dear students, I'm writing T is equal to 0. So initially, time T is equal to 0 when the reaction has not started. Let's assume I have got 10 moles of N2 and 10 moles of H2 present in the container. So if I ask you, how many moles of NH3 would have got formed? Right now, 0. Okay. Now, my dear students, remember, whenever in a question, you will be given with the amounts of all the reactants. Whenever in a question, you will be given with the amounts of all the reactants. Like in this case, we are given with the moles of all the reactants. Right? In another case, mass of all reactants will be given. In another case, volume of all reactants will be given. So in short, whenever you will be given with the amounts of all the reactants, at that time, you will be using the concept of limiting reagent. So when the concept of limiting reagent is used, I'll write it over here. When the amounts of all the reactants when the amounts of all the reactants are given. This is when you use the concept of limiting reagent. Okay. Now, dear students, since we got to know when to use the concept of limiting reagent, now how to use the limiting reagent? The first step always is going to be balancing of the reaction. The first step always is going to be balancing the reaction. Is the reaction balanced? The reaction is not yet balanced. So balance it, make it 3 times, make it 2 times, make it 1. Now the reaction is balanced. After balancing the reaction, we are supposed to identify which one is the limiting reagent. After balancing the reaction, we are supposed to identify which one is the limiting reagent. How do we identify the limiting reagent? There is a special procedure for that. There is a special procedure for that. How do we identify the limiting reagent? Just do one simple thing. Divide the given moles of reactants by their respective stoichiometric coefficients. Like I'm writing 10 divided by 1. 10 divided by 1. Here, it's going to be 10 divided by 3. Divide the given moles of reactants by their respective stoichiometric coefficients. What is the value here? The value comes out to be 10. What is the value here? It comes out to be 3.33. The one which gets the lesser value, that has to be your limiting reagent all the time. Given moles divided by stoichiometric coefficient. The one which gets the lesser value, that will be the limiting reagent. So which one is getting the lesser value? 3.33 is less. So it's going to be H2, which is the limiting reagent. So I hope you got to know how to identify the limiting reagent. So after balancing, we have to identify the limiting reagent. So we have identified in this particular question, the limiting reagent is H2. If the limiting reagent is H2, so N2 has to be the excess reagent. Okay. Now, H2 is the limiting reagent. It would have got completely consumed in the reaction. We started with 10 moles of limiting reagent. We started with 10 moles of H2. After some time, you will find some 0 moles of H2 in the container. It would have got completely consumed. And at that point of time, the reaction would have stopped. The reaction would have stopped. When the reaction would have stopped, since N2 is the excess reagent, so out of 10 moles of N2, there will be some moles of N2 left in the container when the reaction would have stopped. Similarly, there would be some moles of NH3 which would have formed in the container. Okay. Now the point is how to check how many moles of NH3 have got formed. How to check how many moles of N2 are still left in the container when the reaction stops. How do we do that? Have a look. Have a look, guys. First of all, let's talk about the calculation of products. Calculation of moles of products. This is the first application of it. Calculation of moles of products. I need to calculate the number of moles of NH3 formed. Have a look how am I going to do that. Number of moles of NH3 formed. First of all, let me tell you, the entire product formation is decided by the limiting reagent. Limiting reagent is the one which decides the entire product formation. What I'll be doing, since I need to calculate the moles of NH3 formed, I'll be relating the stoichiometric coefficient of limiting reagent with this product. Here it's 3, here it's 2. Now we use the mole method. Can I say, from the stoichiometry, I can say 3 moles of limiting reagent. 3 moles of limiting reagent. It gives 2 moles of NH3. It gives 2 moles of NH3. So, 1 mole of limiting reagent should give me 2 by 3 moles of NH3. But as per the question, did we start with 1 mole of H2 or 10 moles of H2? We started with 10 moles of H2. So, I would say 10 moles of H2 should give 2 by 3 multiplied by 10. The value is 6.66 moles of NH3. So, finally, you got to know that 6.66 moles of NH3 have got formed at the end of the reaction. My dear students, do remember? Entire product formation is decided by the limiting reagent. You'll be always starting with the limiting reagent, number 1. Okay. Now, the second application is calculation of, let me erase all this. I hope this is clear. The second application is, what is that? That is the calculation of moles of excess reagent left. This is one more application of it. Limiting reagent is going to let you know how many moles of excess reagent are left in the container. You started with 10 moles of N2. Now finally there will be some moles of N2 left in the container. Limiting reagent is going to let you know about that. How exactly? Have a look. Just relate the stoichiometry of the limiting reagent with N2 now. Here it's 3, here it's 1. So can I say 3 moles of H2 as per the stoichiometry, 3 moles of H2 reacts with 1 mole of N2. Right? I can say something like this. 3 moles of H2 reacts with 1 mole of N2. Now, dear students, if 3 moles of H2 reacts with 1 mole of N2, can I say 1 mole of H2 reacts with 1 by 3 moles of N2? Unitary method. But did we start with 1 mole of H2? No, we started with 10 moles of H2. So can I say 10 moles of H2 would have reacted with 1 by 3 multiplied by 10. The value will be 3.3 moles of N2. So can you let me know what this 3.3 is all about? Can you let me know what this 3.33 is all about? Can I say these are basically the moles of N2? These are the moles of N2 which have reacted with 10 moles of H2. So you got to know that 10 moles of H2 are reacting with 3.33 moles of N2. How many moles of N2 did I take? I had taken some 10 moles of N2. Out of 10 moles of N2, how many moles of N2 are reacting? 3.33. So out of 10 moles, 3.33 are reacting. So 6.66 moles of N2 will be still left in the container as such. I hope you got it. I hope you got it. Quickly in the chats if you got it. Quickly. So I taught you 2 things. Calculation of moles of products. Calculation of moles of excess reagent left. Now guys, it's not necessary that they'll ask you to calculate moles. They can ask you mass, they can ask you volume, they can ask you molecules, right? But if they ask anything, first you have to calculate these moles. For example, you got to know that at the end of the reaction, 6.66 moles of NH3 are being formed. Now moles multiplied by molar mass of NH3, that gives you the mass of NH3 formed. Moles multiplied by 22.4 liters, that gives you the volume of NH3 formed at STP. Moles multiplied by Avogadro's number, that gives you the number of molecules of NH3 formed, right? Similarly, these are the moles of N2 left in the container. Moles multiplied by molar mass of N2, that gives you the mass of N2 left. Moles multiplied by Avogadro's number, that gives you the molecules of N2 left in the container, right? All these things can be asked. But to calculate all these things, you should have the data for moles. Perfect. So let me quickly recap it. Whenever in a reaction, the amounts of all the reactants are given, we use the concept of limiting reagent. In the limiting reagent concept, we are supposed to balance the reaction first. After balancing the reaction, identify the limiting reagent. How? Divide the moles by the respective stoichiometric coefficients. The one which gets the lesser value, that has to be your limiting reagent. Limiting reagent is the one which decides the entire product formation. Limiting reagent is the one which decides how many moles of excess reagent have reacted. Yes? Perfect. If this is perfect, this question though you should kill. Tell me in this particular reaction, which one is your limiting reagent? Reaction is given and it's given in balanced format. And as per the question is concerned, initially, we have got 3 moles of NaOH and we have got 4 moles of H2SO4. This will be 0, this will be 0, right? Now, dear students, have a look. Amounts of all the reactants are given. So which concept? Limiting reagent concept. The first step is to balance the reaction. It's balanced. After balancing, what do we need to do? Identify. How? Divide the given moles by the respective stoichiometric coefficients. So it's 3 divided by 2 and it's 4 divided by 1. This value will be 1.5. This value will be 4. The one which gets the lesser value, that has to be the limiting reagent. So it's NaOH here, which is the limiting reagent. Done, understood? Right? Done, understood? I hope this is clear. All right. One more question. You should kill these questions now, people. One more. The reaction is already given in the balanced format. Let me write it. 6 times LiH plus 8 times BF3, it gives 6 times LiBF4 plus B2H6 plus B2H6. The reaction is already given in the balanced format. Now, as per the question, on starting with 2 moles each of reactants, how many moles of B2H6 can be produced? How many moles of B2H6 can be produced? You have to calculate the moles of B2H6 formed. Now, dear students, I'm again given with the amounts of all the reactants. Which concept? Limiting reagent concept, right? And in the limiting reagent concept, we are supposed to balance the reaction. It's balanced. Now, identify the limiting reagent. Given moles, divide by stoichiometry coefficients. So, 2 divided by 6 and 2 divided by 8. Now, which value comes out to be lesser? What do you think? 2 by 6 is less or 2 by 8 is less? 2 by 8 is less. The one which gets the lesser value, that has to be the limiting reagent. So, basically, it's BF3 which is the limiting reagent. If BF3 is the limiting reagent, after some time, you'll find some 0 moles of BF3 left in the container. Now, entire product formation, that is decided by BF3, right? Now, what do I need to calculate? I need to calculate the moles of B2H6 formed. So, just relate the stoichiometry of limiting reagent with B2H6, right? So, can I say 8 moles of limiting reagent gives 1 mole of B2H6? I'll write it here. 8 moles of limiting reagent produces 1 mole of B2H6, right? So, can I say 1 mole of BF3, 1 mole of limiting reagent, it produces 1 by 8 moles of B2H6? Absolutely. But did I start with 1 mole of BF3? No. We started with 2 moles of BF3. So, 2 moles of BF3 should produce 1 by 8 multiplied by 2. The value will be 0.25 moles of B2H6. So, finally, you got to know that 0.25 moles of B2H6 would have got formed at the end of the reaction. Similarly, can you tell me how many moles of LiBF4 would have got formed? Simple. 8 moles gives 6 moles. So, 1 gives 6 by 8. 2 gives 6 by 8 multiplied by 2. So, these are the moles of LiBF4 which would have got formed. Anyways, this is not supposed to be calculated, right? Only this thing we had to calculate, but I'm just telling you. Similarly, this LiH, this is the excess reagent. You can calculate the moles of excess reagent left also in the container, correct? First, you'll see how many moles of LiH have reacted. Then, initial moles minus the reacted moles of LiH. That's it. Simple. 8 moles reacts with 6 moles. So, 1 mole reacts with 6 by 8. 2 moles reacts with 6 by 8 multiplied by 2. 6 divided by 8 multiplied by 2 is 12 by 8. 12 by 8 is 3 divided by 2, 1.5. So, basically, 1.5 moles of LiH would have reacted. And I started with 2 moles. So, 2 minus 1.5 comes out to be 0.5. So, 0.5 moles of LiH will be left as such at the end of the reaction. I hope this is clear. All clear? Let's try to do one more question, guys. Let me give you one question. Okay, let me give you one question. The question is like this. On starting with 10 moles each of BaCl2 and Na3PO4 and Na3PO4. Calculate the moles of Ba3PO4 whole twice formed. Can you do it? Say yes or no in the chats. Can you do it? Say yes or no in the chats. Can you do it? Can you do it? Yes or no? Perfecto. Or we guys directly saying no. At least try it. Change your confidence, change your attitude towards learning, right? Don't directly say no. All right, have a look, people. As per the question is concerned, BaCl2 is reacting with Na3PO4, right? So first of all, BaCl2, when it reacts with Na3PO4, what does it give? It gives Ba3PO4 whole twice. This is the reaction which I gave you in the last session as well. With this, you'll be getting NaCl as well. Okay, this is the reaction. Now, dear students, initially at time t is equal to 0, we are starting with 10 moles each of reactants. 10 moles each of reactants. So this has to be 0, this has to be 0. Now, as per the question, amounts of all the reactants are given. So which concept? Limiting reagent concept. Right? Limiting reagent concept. Yeah? Yes, Harini, you can do that. It will be beneficial for you. So, in the limiting reagent concept, what do we need to do? We are supposed to balance the reaction. So balance it. This has to be 3 times. This has to be 2. This will be 1. And this will be 6. The reaction is balanced. After balancing the reaction, what do we need to do? Identify the limiting reagent. Given moles by stoichiometry coefficient. 10 by 3, 10 by 2. 10 by 3 is less. So BaCl2 has to be the limiting reagent. If BaCl2 is the limiting reagent, after some time, when the reaction stops, you'll find some 0 moles of BaCl2 left in the container. Now, what do we need to calculate? Moles of Ba3PO4 whole twice formed. Entire product formation is decided by the limiting reagent. Have a look. This is 3 here. This is 1. So can I say 3 moles of BaCl2 produces 3 moles of BaCl2 produces 1 mole of Ba3PO4 whole twice. Okay. So that means 1 mole of BaCl2 produces 1 by 3 moles of Ba3PO4 whole twice. But did we start with 1 mole of BaCl2? No, we started with 10 moles of BaCl2. So I must say 10 moles of BaCl2 produces 1 by 3 multiplied by 10. The value comes out to be 3.33. So these are the moles of Ba3PO4 whole twice which have got formed at the end of the reaction. Yeah? That's something which we were supposed to calculate. I hope you can solve all the questions from now onwards related to the limiting reagent. Yeah? One more question. This is your homework. I'm just giving you the reaction here. This is your homework. H2SO4 plus NaOH. It gives Na2SO4 plus water. Okay? This is the reaction. And as per the question, you are not given with the moles of reactants. You are given with the masses of reactants. That's completely okay. We know how to convert masses into moles, right? We can do that. 160 grams of NaOH means 4 moles of NaOH. 98 grams of H2SO4 means 1 mole of H2SO4. So indirectly we are given with moles only, right? We are given with 4 moles of we are given with 1 mole of H2SO4 and 4 moles of NaOH. Now, this has to be 0. This has to be 0. Now, what all things you have to calculate here? You will be doing the calculations and you will be letting me know the answers of all the questions in the comments afterwards, okay? First of all, you have to identify. You'll be telling me which one is the limiting reagent. Identify the limiting reagent, okay? Tell me the moles of Na2SO4 formed, okay? You need to tell me the mass of Na2SO4 formed. Once you calculate moles of Na2SO4, just multiply that with molar mass, get it done. Okay. Similarly, tell me the moles of excess reagent left in the container at the end. These are some 2-3 assignments which I'm giving you. Okay, just give them a try and let me know its answer in the comment section afterwards. Okay, perfect. So people, I want that confidence. If the question comes from the limiting reagent, will you be able to solve it? Say yes or no, everyone in the chats, quickly. Say yes or no in the chats, quickly. Quickly, people. I want to hear it from everyone. If the question comes from the limiting reagent, will you be able to solve it? Yeah? I want everyone, whosoever is watching me right now, I want everyone to say it, either yes or no. Quickly. Quickly, people. Yes, Harini, you'll be getting that. The chats are really slow. I want the chats to move fast. Why are chats running so slow? Say yes or no, quickly. Is the Josh decreasing day by day? Yeah? Don't do that at all. Perfect. Let's move on now. Let's now move on to one more concept. What is that? Let's do the percentage yield concept. One more simple basic concept, okay? Percentage yield. Frequently questions are asked from percentage yield, okay? So people, before letting you know the meaning of percentage yield, what it exactly means, I'll first of all give you its formula, okay? I'll give you its formula. I'll show you how to calculate the percentage yield. And at the end, I'll let you know what it exactly means, okay? First, I'm going to give you the formula. I'll show you how to apply the formula. And then, at the end, I'll let you know what is the meaning of it, okay? This is going to be the sequence here. So first of all, percentage yield. What is the spelling? Y-I-E-L-D, yeah? Is always equal to experimental or actual amount divided by expected or theoretical amount multiplied by 100. This is one general formula. This is one general formula by means of which we can calculate the percentage yield. Now, dear students, one thing. In order to calculate the percentage yield of the reaction, we should have two amounts: experimental, expected. Now, this expected amount, which you also call as theoretical amount, right? We always calculate it with the help of stoichiometry. And mainly, which method in stoichiometry will be using? We'll be using the mass method in stoichiometry to calculate what? To calculate the expected amount. The point is how. So, just to make you understand this concept properly, I'll directly start with a question so that you'll properly understand what it means and how it's to be calculated. Okay? So, starting with the first question, basic question. The question says, on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was produced. Calculate the percentage yield of the reaction. So first of all, the reaction is like this. We know calcium carbonate upon heating, it gives calcium oxide, and with calcium oxide, you get carbon dioxide as well. Now, my dear students, in the question, they are telling us that upon heating 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So this is something which has been verified in the lab itself, right? This is something which has been verified in the lab. This is something which has been verified experimentally, that when you actually heat up calcium carbonate in the lab, it will give you 20 grams of calcium oxide. So if I ask you whether this 20 grams, it is the experimental amount or expected amount? It is the experimental amount. It has been observed experimentally that 20 grams of calcium oxide is obtained in the lab. Okay? Right? This is the experimental amount. My dear students, in order to calculate the percentage yield, how many amounts do we need? First, we need the experimental amount. divided by, we need the expected amount multiplied by what? Multiplied by 100. Already this experimental amount is given to us. Yeah? What do we need now? We just need expected amount. How do we calculate the expected amount? With the help of stoichiometry. Which method? Mass method. If you want to use the mole method or mass method, what do you need to do? Balance the reaction. The reaction is already balanced, right? The reaction is already balanced. Okay? Now understand. What is the mass of 1 mole of calcium carbonate? Its molar mass. That's 100 grams. 100 grams of calcium carbonate upon heating. What is the mass of 1 mole of calcium oxide? 56 grams. So basically, can I say, from the stoichiometry, I'm getting the idea basically. From the stoichiometry, I'm getting the idea that 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide. I'm using the term should produce. This is something which is a theoretical data, which I'm writing on board. That stoichiometry is telling us that 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide. That means 1 gram of calcium oxide, 1 gram of calcium carbonate should produce 56 divided by 100 grams of calcium oxide. Yes. But do I have 1 gram of calcium carbonate or 40 grams? 40 grams. So as per the question, 40 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 40. The value comes out to be 22.4 grams of calcium oxide. Now you tell me, what is it? What did I calculate? What is this term? This is basically the mass of calcium oxide which should have got produced upon heating 40 grams of calcium carbonate. So this is something which I was expecting to get formed, this much. I was expecting this much amount of calcium oxide to get formed. So this is my expected amount here, which I calculated with the help of what? With the help of stoichiometry, right? In order to calculate percentage yield, how many amounts do we need? 2. Experimental, we already have. Expected, we calculated. Done, right? So percentage yield of the reaction will be experimental divided by expected multiplied by 100. When you solve it, the value comes out to be 89%. If I ask you what is meant by this 89%, 89%, it is basically the percentage yield of the reaction. It is the efficiency of reaction. What does it mean? It means 89%. 89% of the expected amount. 89% of the expected amount is actually getting formed. When you calculate this term, see, 89% of expected amount. When you solve it, you'll exactly find out to be equal to experimental. Okay? This 20 grams, it was the experimental amount. It was the actual amount. So 89% of the expected amount is actually getting formed. I hope you're getting it. How there 56? Calcium 40, oxygen 16. 40 plus 16, 56. I hope this is clear, people. Quickly in the chats. Quickly, people. Sahil Sahab, this is the English channel. You can read the name of the channel. It's Unacademy NEET English. So I'm not supposed to talk in Hindi or Urdu. Is it clear, guys? Quickly. Should we move on to one more question? Yeah? Should we solve more questions on this? Should we solve more questions on this quickly? Yes or no in the chats, everyone? Perfect. Let's try to solve a few more questions. Let's try to solve a few more questions. Okay. As per the question is concerned, a 15.6 grams of benzene 15.6 grams sample of benzene is mixed with excess of HNO3 in presence of H2SO4 and 18 grams of nitrobenzene is obtained. Calculate the percentage yield of the reaction. Read the question carefully, guys. I want you guys to read the question. The question says 15.6 grams of benzene when mixed with HNO3 produces what? 18 grams of nitrobenzene. So this is something again which has been seen experimentally in the lab, that 18 grams of nitrobenzene is being formed. So what is this basically? This is your experimental amount. This has been experimentally observed, that 18 grams of nitrobenzene being formed in the lab. 15.6 grams of benzene on reaction with HNO3. It produces what? As per the question, it produces 18 grams of nitrobenzene. So I got the experimental amount. What do I need now? I need the expected amount, which we get with the help of stoichiometry. Which methods? Mass method. Now, the reaction is already balanced. Now relate them. What is the mass of 1 mole of benzene? It's 78 grams. So 78 grams of benzene gives. What is the mass of 1 mole of nitrobenzene? Can you calculate it? This will be 77. 77 nitrogen will be 14. 91 and 32, 123. Okay. So the mass of 1 mole of nitrobenzene, which is its molar mass, which is 123 grams of nitrobenzene. Okay, perfect. My dear students, can I say stoichiometry is giving me the idea that from 78 grams of benzene, 123 grams of nitrobenzene should get produced. Who's telling me that? Stoichiometry is giving me the idea about that. That from 78 grams of benzene, 123 grams of nitrobenzene should get produced. So, 1 gram of benzene should produce 123 divided by 78 grams of nitrobenzene, right? 1 gram of benzene should produce this much. That means 15.6 grams of benzene should produce 123 divided by 78 multiplied by 15.6 grams of what? Nitrobenzene. Correct? When you solve this, you'll be getting the value exactly as 24 grams. 24 grams of what? Nitrobenzene. Can you let me know what is the meaning of this term? Basically, this is the mass of nitrobenzene which should get formed. This is the mass of nitrobenzene which should get formed from 15.6 grams of benzene. So this is something which I was expecting. This much amount of nitrobenzene I was expecting to get formed through stoichiometry. So, can I say this is basically the expected amount? This is basically the expected amount, right? How many amounts did I need? I needed 2 amounts. Experimental, expected, right? In order to calculate the yield, I would say percentage yield will be equal. Experimental amount, 18 grams. Expected amount, 24 grams, multiplied by 100. Solve it, the value comes out to be 73%. So what this 73% is all about now? 73 or 75, something around that, yeah? So this 75%, it is the yield of the reaction. That means 73% of the expected amount is actually getting formed. 73% of 24 will be exactly equal to 18. Yeah? Perfect. Is it clear? Is it clear? Are you getting the confidence that you can solve all the questions from percentage yield? Quickly, people. Quickly. One more question. First of all, the reaction is given to us. What is the reaction? Calcium oxide plus 2 times HCl. What does it give? It gives CaCl2, and with the CaCl2 we have water as well. The reaction is already given in the balanced format, right? The reaction is already given in the balanced format. Now the question says 1.12 grams. Guys, it is a similar question, same type. I think you can do this question on your own. The question is of similar type, right? Can you do this on your own? 1.12 grams of calcium oxide, it gives 1.776 grams of CaCl2, right? So this is your experimental amount. Now you will calculate the expected amount of CaCl2 with the help of stoichiometry. It is a similar question. So this should be your homework question only, right? Because it's simple. It's the same. It is of the same pattern. You can solve it. I'll show you some different question. Wait. Okay, let's have a look on this one. Look at this one. On heating, 150 grams of calcium carbonate. So as per the question, we are heating 150 grams of calcium carbonate. What mass of calcium oxide is produced if the yield of the reaction is 75%? The yield of the reaction is 75%. And we are heating 150 grams of calcium carbonate. We need to calculate the mass of calcium oxide produced. How exactly are we going to do that? First of all, let's try to write the reaction. Calcium carbonate, upon heating, produces calcium oxide. With this, you are going to write carbon dioxide. The reaction is already balanced. Okay. The yield of the reaction is 75%. Right? Now, the mass of 1 mole of calcium carbonate, that's 100 grams. 100 grams. The mass of 1 mole of calcium oxide, that's 56 grams. Okay. So, as per the question is concerned, 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide. So 1 gram of calcium carbonate upon heating should produce 56 divided by 100 grams of calcium oxide. Correct? That means 150 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 150 grams of calcium oxide. This value approximately, it will come out to be 84 grams. Now, what this 84 grams is all about? That's my question to you. That's my question to you. What this 84 grams is all about? This is the mass of calcium oxide which I was expecting to get formed. This is the mass of calcium oxide which I was expecting to get formed. But the yield of the reaction is not 100%. The yield of the reaction is not 100%. If the yield of the reaction was 100%, then whatever was expected, same would have been actual, right? So, if I ask you, the actual mass of calcium oxide will be equal to 75% of expected amount is actually being formed, right? This is the actual amount of calcium oxide which we were supposed to calculate. Is this clear? Is this clear to everyone, people? So one more concept is done and dusted, right? One more concept is done and dusted. Clear to everyone quickly? Yes, everyone in the chats. Is it super clear? Is it super clear, people? Quickly. Wonderful. Let's have a look on one more concept then. Let's have a look on one more concept. Percentage purity. Percentage purity. Okay. Let's see what kind of questions are asked from this and what it means exactly. First of all, I'll make you understand what this percentage purity is all about. Or let me write one result, okay? Let's leave it aside. Let me write a result directly first of all. I'm writing something as percentage purity. Percentage purity of a compound. Percentage purity of a compound in an impure sample. Percentage purity of a compound in an impure sample. In an impure sample is equal to mass of pure compound divided by the mass of impure sample multiplied by 100. Now you must be thinking, what is mass of pure compound? What is the mass of impure sample? Let me make you understand this a bit. See, for example, this is the container which I have. Let's say this is the container which I have, okay? This is the container, for example. Now, dear students, in this container, for example, I'm keeping calcium carbonate plus something. I have no idea what this something is all about. ABC I'm keeping. I have kept calcium carbonate. With the calcium carbonate, I have kept some other things as well. These other things over here in the container, I'm calling them as the impurities. Whatever is there in the container except calcium carbonate. Whatever there is there in the container except calcium carbonate. I call it as the impurity. Okay. So in the container, what do we have? We have calcium carbonate plus impurities. We have calcium carbonate plus impurities. Okay. Now, if I ask you, this whole sample in the container, should I be calling this as pure sample of calcium carbonate or impure sample of calcium carbonate? This whole sample present in the container, I'll be calling this as the impure sample of calcium carbonate. I'll be calling this as the impure sample of calcium carbonate, right? Now, my dear students, let's assume the mass of whole impure sample. The mass of whole impure sample is, for example, 50 grams. This is the mass of whole sample. Okay. Let's assume out of 50 grams, we have got almost 20 grams, which is basically the mass of pure calcium carbonate. Okay. Let's assume out of 50 grams in total, 20 grams is the mass of pure calcium carbonate. If I ask you, what is the percentage purity of calcium carbonate in the sample? If I ask you what is the percentage purity of calcium carbonate in the sample, you will say mass of pure compound, mass of pure calcium carbonate, that is 20 grams, divided by mass of impure sample, that's 50 grams, multiplied by 100. Whatever value comes out to be, that is basically percentage purity. That's percentage purity of calcium carbonate in the sample. Right? How much this value comes out to be? So it will be 40, right? It will be 40. Percentage purity of calcium carbonate in the sample is 40. What does that mean? What does that mean? That means 40 grams. That means 40 grams of pure calcium carbonate are present in 100 grams of the impure sample. I hope you are getting. Percentage purity of calcium carbonate in the sample came out to be 40. What does that mean now? That means 40 grams of calcium carbonate, of pure calcium carbonate, is present in 100 grams of impure sample. Okay? So you can write out its definition as well. So I started with the formula, no doubt. But first, I would want you guys to write its definition. Percentage purity of a compound in the sample. What does that mean? That means it is defined as that mass of the pure compound in grams which is present in 100 grams of its impure sample. Which is present in 100 grams of its impure sample. Okay? Right? And simplest way to calculate the percentage purity, this is the formula. Now let's try to apply it and let's try to see what kind of questions can be asked and how the questions are to be solved. But before solving the question, do remove a few points. Point number 1. In a chemical reaction, only pure substance participates. In a chemical reaction, only pure substance participates. That means impurities, they do not participate in the reaction. Impurities do not participate in the chemical reaction. Number 1. Number 2, there is one type of the statement which I'm going to write over here, and you should know how to decode that statement. The statement is something like this. For example, 50 grams of 80% pure calcium carbonate. What does it mean? 50 grams of 80% pure calcium carbonate. What does it mean? It means this 50 grams is the mass of the impure sample, the mass of whole sample. And out of 50 grams, if you want to calculate the mass of pure calcium carbonate, how you are going to do that? 80% of 50. 80 divided by 100 multiplied by 50. The value comes out to be 40 grams. So 40 grams is basically the mass of pure calcium carbonate present in 50 grams of the impure sample. I hope this type of a statement you can easily decode from now onwards. Yeah? Let me give you one more. Let me give you one more. For example, I'm writing a statement like this. You tell me what is its meaning. 70 grams of 50% pure. 50% pure NaCl. What does that mean? So this 70 grams, this is the mass of whole impure sample. It is 70 grams. Okay? So what is the mass of pure NaCl? Mass of pure NaCl is going to be 50% of 70. So 50 divided by 100 multiplied by 70. The value comes out to be 35 grams. So 35 grams is the mass of pure NaCl. Yeah? Yes, Ahmad Iqbal, yes, whole syllabus will be completed. Relax, no worries. People, all these things are clear? Say yes or no. Now I'm going to start the questions so that you can understand and analyze it properly, quickly. Yeah? All clear? If this is clear, let's try to do some questions so that you can understand all these concepts properly. And let's see what kind of different questions can be asked. Number one, 50 grams of 80% pure calcium carbonate. So first of all, in a chemical reaction, only pure substance participates. So only pure calcium carbonate has to participate in the reaction. So it's better to calculate the mass of pure calcium carbonate. So in this 50 grams of the whole sample of calcium carbonate, what is the mass of pure calcium carbonate? What is the mass of pure calcium carbonate? It is 80% of 50. The value comes out to be 40 grams. So basically, we have got 40 grams of pure calcium carbonate, right? Yeah. So this is basically the mass of pure calcium carbonate present in 50 grams of the whole sample, right? 50 grams of the whole sample. Perfect. Okay, if I ask you, how many pure moles of calcium carbonate are there in the sample? You'll say pure mass of calcium carbonate divided by molar mass of calcium carbonate. So these are the pure moles of calcium carbonate in the sample. And we know in a chemical reaction, only it's the pure substance which participates, right? Now look at the question. Upon heating calcium carbonate, calculate the volume of carbon dioxide produced. So we know when calcium carbonate is heated, what does it produce? Calcium oxide. And with this calcium oxide, carbon dioxide gas is produced. The reaction is already balanced. The reaction is already balanced. Now can I say 1 mole of calcium carbonate upon heating? 1 mole of calcium carbonate upon heating produces 1 mole carbon dioxide. 1 mole calcium carbonate upon heating produces 1 mole carbon dioxide. So therefore, 0.4 moles of pure calcium carbonate upon heating, it will produce 0.4 moles of carbon dioxide. So what did I calculate till now? I calculated the number of moles of carbon dioxide produced. That's 0.4. So my dear students, was I supposed to calculate moles of carbon dioxide produced? No. I'm supposed to calculate volume of carbon dioxide produced at STP, which will be equal to moles multiplied by 22.4 liters. The value comes out to be 8.96 liters. So this is the volume of carbon dioxide which will be produced at the end. I hope this is clear. I hope this is clear. Quickly in the charts. This is the volume of carbon dioxide which will be getting produced at the end, right? And see, in the reaction, it is not 50 grams which are participating. It is 40 grams which are participating. It is 0.4 moles which are participating. That's why I told you one statement. In a reaction, only pure substance participates. Impurities, they do not participate in the reaction. Okay? Perfectly done? All right. If this is clear, let's try to solve one more question. Let's try to solve one more question. Just a second. Let's start with this question first. Let's do this question first. Read the question carefully, guys. 5 grams of H2SO4 sample. Okay, just read it carefully. It's mentioned that H2SO4 sample, 5 grams of H2SO4 sample. That means, is this 5 grams? Is this 5 grams the mass of pure H2SO4, or this is the mass of whole sample? This is the mass of whole sample of H2SO4. It has to be the mass of impure sample of H2SO4. It has to be the mass of impure sample of H2SO4. Correct? One thing which I understood till now. 5 grams of H2SO4 sample exactly requires 4 grams of NaOH. 4 grams of NaOH for neutralization. Calculate the percentage purity of H2SO4 in the sample. So basically, I need to calculate the percentage purity of H2SO4 in the sample of H2SO4. So it will be equal to mass of pure H2SO4, right, divided by mass of impure sample of H2SO4 multiplied by what? Multiplied by 100. Multiplied by 100, right? Clear? Now, people, what is the mass of impure sample of H2SO4? That's 5 grams. Already we know this thing. This is 5 grams. What is the mass of pure H2SO4? What is the mass of pure H2SO4? We have to calculate that. See, for that, I'll be writing the reaction again. H2SO4 plus 2 times NaOH, it gives Na2SO4 plus 2 times water. One thing I would ask you, can I say that mass of H2SO4 which would have participated in the reaction? That mass of H2SO4 which would have participated in the reaction. Can I say that is going to be the pure mass of H2SO4? Because in a reaction, only pure substance participates. So I'll be using the stoichiometry, and with the help of stoichiometry, I'll get to know how many grams of H2SO4 have participated in the reaction. Right? I'll get to know how many grams of H2SO4 have participated in the reaction with the help of stoichiometry. That gives me the pure mass of H2SO4. Okay? Now, first of all, have a look. What is the mass of 2 moles of NaOH? It's 80 grams. I'll say, as per stoichiometry using the mass method, 80 grams of NaOH reacts with 1 mole of H2SO4 means 98 grams of H2SO4. I can write this kind of a statement. Correct? 80 grams of NaOH reacts with 98 grams of H2SO4. So 1 gram of NaOH reacts with 98 divided by 80 grams of H2SO4. Right? 1 gram of NaOH reacts with 98 divided by 80 grams of H2SO4. If 1 gram of NaOH reacts with these many grams, what about 4 grams of NaOH? 4 grams of NaOH reacts with 98 divided by 80 multiplied by 4. The value comes out to be 4.9 grams of H2SO4. Now you just ask yourself that what did we calculate here? What is it? Just ask yourself, what is it? Just ask yourself, what is it? This is the mass of H2SO4 which has reacted with 4 grams of NaOH. So with 4 grams of NaOH, 4.9 grams of H2SO4 have reacted. And that mass of H2SO4 which has reacted in the reaction, that's basically the pure mass of H2SO4. That's basically the pure mass of H2SO4. Correct? Now calculate the percentage purity of H2SO4 in the sample, which is equal to pure mass of H2SO4 divided by impure mass of sample multiplied by 100. The value comes out being 98%. So this particular sample which we took in the beginning, 5 grams of H2SO4 sample, the percentage purity of H2SO4 in this sample is how much? In this sample, that's 98%. What does that mean? That means in 100 grams of sample, you will find 98 grams of pure H2SO4. In 100 grams of sample, you will find 98 grams of pure H2SO4. Quickly in the chats, if it's clear. Quickly, people. Yeah? Perfectly done? All right. Let's try to solve one more question. Okay, one more question. Check this question carefully. It's again simple. Yes, friends forever, yes. Look at this question, guys. 410 grams of limestone, right? So we have got limestone, which is calcium carbonate plus something else. Okay, leave that aside. So basically, should I be calling this 410 grams as the mass of impure sample of calcium carbonate? It is the mass of limestone. Limestone consists of calcium carbonate plus something, right? So what is it going to be? So this 410 grams, it is the mass of impure sample of calcium carbonate, right? Now, 410 grams of limestone is treated with oxalic acid to produce 12 grams of calcium oxalate. Calculate the percentage purity of calcium carbonate in the limestone sample. So in this limestone sample, we have to calculate the percentage purity of calcium carbonate. Okay? So I'll say percentage purity of calcium carbonate in the sample is equal to, it's going to be mass of pure calcium carbonate in the sample divided by mass of whole sample, mass of impure sample multiplied by 100. Mass of impure sample of calcium carbonate. And mass of impure sample of calcium carbonate, already we have 410 grams. So we need to calculate the mass of pure calcium. Now the point is, how do we calculate the mass of pure calcium carbonate? Understand properly. So first of all, in this particular reaction, here you can see calcium carbonate. So by using stoichiometry, I'll calculate the mass of calcium carbonate which has participated in the reaction. By using the stoichiometry, I'll calculate that mass of calcium carbonate which has participated in the reaction. Correct? And we know any such mass of reactant which participates in the reaction, that's always going to be its pure mass. Yeah? So what I'll be doing? The reaction is already balanced. Here it's 1, here it's 1. What is the mass of 1 mole of calcium oxalate? How much that will be? 40 plus 24, 64, 60 plus 64, 64, 128. So I'll write 128 grams of calcium oxalate. This is calcium oxalate. 128 grams of calcium oxalate are produced from 100 grams of calcium carbonate. Right? 100 grams of calcium carbonate. That means 1 gram of calcium oxalate is produced from 100 divided by 128 grams of calcium carbonate. Right? So 1 gram of calcium oxalate is produced from these many grams of calcium carbonate. That means 512 grams of calcium oxalate is produced from 100 divided by 128 multiplied by 512. The value comes out to be 400 grams of calcium carbonate. So what is this term which we got here? This is the mass of calcium carbonate. This is the mass of calcium carbonate which has participated in the reaction. And that mass of calcium carbonate which participates in the reaction, what do we call that as? That's called as pure mass of calcium carbonate. Right? So percentage purity is equal. Pure mass of calcium carbonate is 400 grams. Mass of impure sample of calcium carbonate is 410 grams. Multiply with 100. Solve it. Get the percentage purity of calcium carbonate in the sample. I hope this is clear to everyone. Quickly. With this, your percentage purity is also done. One question I'm giving you as the homework in this one as well. One question as homework. This is your homework question for percentage purity. You are going to give it a try. You are going to give it a try. Okay? You are going to give it a try, people. I hope everything is clear. Now, my dear students, it is time to discuss percentage composition molecular empirical formula. That is going to be the last topic of the chapter. Okay? With the problems. And one more thing. Concentration terms. You would have heard about concentration terms topic. That is something which I teach in solution chapter. Right? That is a part of chapter solution. The concentration terms, I'll be either teaching with solutions or I'll take a separate one shot for concentration terms, because concentration terms are there in mole concept, they are there in solution, they are there in equilibrium as well. So wherever concentration terms are involved, right, I'll take a separate one shot for that. Okay, perfect. Is that cool? Right? Like concentration terms. Normally, what do we study in concentration? Weight by weight, weight by volume, volume by volume, mole fraction, right? Molarity, molarity of dilution, molarity of mixing, of reacting, of non-reacting, of ideal solution, molarity of ions, normality, equivalent mass, everything. That needs a separate one shot. Wherever in your physical chemistry, the concentration terms are included, I'll be covering all those things in that same section. Yeah? Perfect, guys. So let's move on now. So before starting the molecular and empirical formula, there is one more term which you need to know. Second. And what is that term? That is vapor density. One simple term, this is vapor density. Vapor density. Now, what this vapor density is all about? See, guys, I'm writing a statement here. Vapor density of a gas. How do we define the vapor density of a gas? How do we define the vapor density of the gas? Understand. For example, I'm taking two containers. Okay. One container contains a gas over here, some random gas. Okay. And one more container, it particularly contains H2 gas. We have got two containers. One containing some random gas, whatever it is, and one more containing H2 gas. Both the gases are kept at same pressure and temperature. Let's assume density of gas is represented by this term, D gas, and density of H2 gas is represented by this, DH2. DH2 represents density of H2 gas, and D gas, it represents the density of the gas. Both the gases, they are present at same pressure and temperature. Now the point is, how do I define the vapor density of the gas? Vapor density of the gas is nothing, it's simple. It's basically defined as the ratio of, density of the gas to that of density of H2 gas. At same pressure. Simple. Whatever is the density of gas, divide the density of the gas with the density of H2 gas, provided both the gases are present at same pressure and temperature. Whatever value you'll be getting from this, that's going to give you the vapor density of the gas. Yeah? Voice delay. Is the voice not in sync with what I'm saying? Let me just check it. Wait. Hello. What's up? How are you? Hello. It's fine, but it's not that much of lag. Relax. You are creating issue as if you are unable to see anything, unable to hear anything. It's perfect. It's manageable, right? It's manageable. So basically, if you want to define the vapor density of a particular gas, it's always defined as density of the gas divided by density of hydrogen gas, provided both the gases are present at same pressure temperature. Yeah? Number one. Number two, all of you would have studied this particular formula. PM is equal to DRT, density form of ideal gas equation. All of you must be knowing density form of ideal gas equation. Since keeping pressure and temperature constant, R is already constant. Can I say molar mass is directly proportional to density? Yes, molar mass is directly proportional to density. So wherever in this particular equation, which is written at constant pressure and temperature, wherever in this equation you are seeing the term density, you can replace the density by the term molar mass. So I can say vapor density of the gas is equal to density of the gas means I'll be writing molar mass of the gas. Density of H2 means molar mass of H2. Correct? So I can say vapor density of the gas is equal to molar mass of the gas divided by, what is the molar mass of H2? That's 2 grams per mole. So from this particular one, you are getting an equation. What is the equation? The equation is molar mass of the gas is always equal to 2 times the vapor density of the gas. So sometimes you will be given with a gas. You will be given with a gas whose vapor density will be given. You just have to multiply vapor density by number 2. You'll be getting the molar mass of it. Nothing else. Okay? Perfect. So vapor density of any gas multiplied by number 2, that gives you the molar mass of that. I hope that's clear. I'll show its application in a while. Just wait for it. One more thing, guys. One more thing. For example, if you'll be having a mixture of gas, for a mixture of gas, I would say for a mixture of chemically non-reacting gases. Let's say this is the container, and this particular container, it contains, let's say, 2 chemically non-reacting gases, gas 1 and gas 2. Okay, gas 1 and gas 2. Perfect. Now, first of all, since it's a mixture of gas, it's a gaseous mixture. It's a gaseous mixture. And for a gaseous mixture, what do we define? Do we define the normal molar mass or average molar mass? For the gaseous mixture, we always define average molar mass, right? Perfect. So if I want to write this particular equation for the gaseous mixture, what should I write? Should I write molar mass of the gas or average molar mass of the mixture? Average molar mass of the gaseous mixture is equal to 2 times what? Vapor density of the mixture. 2 times what? 2 times the vapor density of the mixture. This is one more equation. This is one more equation. Okay? This is one more equation. Average molar mass of the gaseous mixture is always equal to 2 times the vapor density of the mixture. So for example, if you'll be having a gaseous mixture, right? If you know its average molar mass, or if you know the vapor density of the gaseous mixture, multiply that by number 2, you'll be getting the average molar mass of the mixture. Yeah? Right? Friends forever, there's a link, enroll now karke. Click on that link and get enrolled. Okay? Perfect. So dear students, let's say exactly what kind of questions can be asked. What kind of questions can be asked? Okay, let's start with a simple question. Let's start with a simple question. Let me give you one simple question. Let's say the question is like this. For example, the question is, calculate the vapor density of the gaseous mixture. Calculate the vapor density of a gaseous mixture containing O2 and O3 in 4:3 molar ratio. In 4:3 molar ratio. This is the question. This is the question, guys. Understand what it says. As far as the question is concerned, let's assume this is the container. And in this particular container, what do we have? We have O2, and with O2, we have O3, right? Let me call this as gas 1. Let me call this as gas 2. So molar mass of gas 1 is 32 grams per mole. Molar mass of gas 2 is 48 grams per mole. Both the gases, they are present in the molar ratio of 4:3. both the gases are present in the molar ratio of 4:3. That means if the moles of O2 are 4x, so moles of O3 are supposed to be 3x. So this has to be N1, this has to be N2. Correct? Clear till here? What are we supposed to calculate? The vapor density of the mixture. Few minutes back, I gave you one relation. Average molar mass of the gaseous mixture is always equal to 2 times the vapor density of the mixture. Right? So, vapor density of the mixture has to be equal to average molar mass of the mixture divided by 2. Correct? And dear students, do you remember how do we calculate the average molar mass of the mixture? There were certain results which I gave you, if you remember. A lot of results which I gave you to calculate the average molar mass of the mixture. One of the result was M1N1 plus M2N2 divided by what? Divided by N1 plus N2. Perfect. And in the denominator already 2 is mentioned. So I would say vapor density of the mixture has to be equal to M1, that's 32, N1 is 4x. So 32 into 4x, that is 4 to 8, 4, 3, 12, 128x. Plus M2N2, M2N2, 48 multiplied by 3. How much that comes? 3 8s are 24, 3, 4, 12, 144x, right? Plus 144x divided by, this is 2 times, N1 plus N2, 4x plus 3x comes out to be 7x multiplied by 7x. So x everywhere cancel. So this is 8, 4, 12, 4, 1, 5, 5, 2, 7, 272 divided by 14. So this is basically what? This is your vapor density of the gaseous mixture, which you were supposed to calculate. Yeah? Right, people? Is this clear to everyone? This is the vapor density of the gaseous mixture which we were supposed to calculate. Now, if you ask me whether vapor density has any units or not, density, cancel, right? Yeah? Okay, it does not have any units. Perfecto. One more question. There is one small change which I've done here. And what is the change? In the last question, I gave you the molar ratio. And here, I'm not giving you the molar ratio. I'm giving you the mass ratio. Can you give it a try? Can you give it a try, people? Can you give it a try? Let's try to understand this question also. As far as the question is concerned, for example, I've got a container. Let's say this is the container. And my dear students, in this container, what do we have? We have got O2 gas, and with O2 gas, we have got O3 gas as well. Okay? Right? Dear students, the molar mass of O2 is 32 grams per mole. The molar mass of O3 is 48 grams per mole. This is something which you all must be knowing. Now, as per the question, the mass ratio of these two gases is given. Mass ratio means mass of O2 divided by mass of O3. This value is given to us as 4:3 means 4 by 3. Right? If mass ratio is given, can I convert it into mole ratio? Number of moles of O2 divided by number of moles of O3 is equal to moles of O2 means mass of O2 divided by molar mass of O2. Moles of O3 means mass of O3 divided by molar mass of O3. Now you tell me, WO2 divided by WO3, WO2 divided by WO3, that's given to me as 4 by 3 multiplied by MO3, molar mass of O3, 48 grams per mole, molar mass of O2, 32. Check it out, 41, 48, 31, 316. The value comes out to be 2:1. So the molar ratio of O2 and O3 is coming out to be 2:1. So the molar ratio is 2:1. If the molar ratio is 2:1, let's say the moles of O3 are X, so this has to be 2X. That means this is the value of N1, this is the value of N2. Now after this, the procedure is same. After this, the procedure is same, people. After this, the procedure is same. What is the procedure now? What do we need to calculate? Vapor density of the mixture. Vapor density of the mixture is equal to average molar mass of the mixture divided by 2. Yeah? Average molar mass of the mixture means M1N1 plus M2N2 divided by what? Divided by N1 plus N2. And in the denominator, you have 2. Perfect. Now everything is in front of you. Just kill it. M1, N1, M1, N1. So 32 into 2 comes out to be 64x. Plus M2, N2, 48 into x, right? 48x divided by, this is 2, N1 plus N2. 2x plus x comes out to be 3x. 3 2s are, it comes out to be 6x in the denominator, right? X everywhere gets cancelled. Just solve it, get the answer. That's it. Clear? I hope the term vapor density and the questions which can be asked from it are clear to you. One question from vapor density, I'm giving you as the homework. You guys will be giving it a try. You guys will be giving it a try. Yeah? You guys will be giving it a try. Which formula for M average I was using till now? M1, N1 plus M2, N2 divided by N1 plus N2. You can use the mole fraction formula as well. M1 chi1 plus M2 chi2, etc. Yeah? I hope all these things are clear to you. Perfect. Now guys, something that's called as percentage composition. That's called as percentage composition. Let me just teach you in a very simplified manner. I'm not going to stretch it a lot, right? Let's teach it in a simplified manner. And what kind of simplified manner that's going to be? Have a look. Have a look, guys. Understand properly what I'm going to say. The first part which I'm going to cover here, that is the percentage of element. The percentage of an element in a compound by mass. This is the first topic which we are going to discuss here. Percentage of an element in a compound by mass. What does that mean? That means that mass of the element in grams present in 100 grams of compound. Mass of the element in grams which is present in 100 grams of compound. What does that mean? You'll get the idea in some time. Okay. Before talking about that in detail, whenever I need to calculate the percentage of element in a compound, by mass. How do I do it? Percentage of element in a compound by mass. How do I do it? First of all, I write molar mass of the element. This is the formula. No need to go for the derivation. Voice not clear. What's wrong with the voice? Just a second, guys. Hello? Can you all hear me now? Can you all hear me? Okay, perfect. Now it's perfect, right? Okay. I'm just giving you the result by means of which you can calculate the percentage of an element in a compound by mass. It's always equal to molar mass of the element multiplied by Z divided by molar mass of element multiplied by Z divided by molar mass of compound multiplied by 100. What is the Z here? What is the Z here? Z represents the number of moles of element. Number of moles of element present in 1 mole of compound. Present in 1 mole of compound. Now, what all this means exactly? Okay, I hope you took a note of every single thing. Now, let's understand all this in detail. Let's understand all this a bit more in detail. See, guys, for example, I'm taking the example of glucose. Do you know what is the formula of glucose, molecular formula? It is C6H12O6, correct? C6H12O6. You know it. Yeah? Now, dear students, if I ask you to calculate percentage of carbon in glucose, Can you let me know what am I asking you exactly? Percentage of carbon in glucose, what does that mean? I'm asking you to calculate that mass of carbon which is present in 100 grams of glucose, right? How do we define the percentage of an element? It is defined as that mass of the element which is present in 100 grams of compound. Now I'm asking you to calculate the percentage of carbon in glucose. What does that mean? That means I'm asking you to calculate the mass of carbon in grams that is present in 100 grams of glucose. How do we do that? We have got the formula. What is the formula? Formula is molar mass of the element multiplied by number of moles of element present in 1 mole of compound divided by molar mass of compound. Have a look. Percentage of carbon in glucose is equal to, first term is molar mass of element. Element here is carbon. So molar mass of carbon is 12 grams multiplied by number of moles of element present in 1 mole compound. Now you tell me, in 1 mole glucose, how many moles of carbon are there? 6 moles of carbon divided by molar mass of the whole compound multiplied by 100. It will give you the percentage of carbon in glucose. That's it. People are saying it's 40. So percentage of carbon in glucose is 40. So what does it mean? What does it mean? Percentage of carbon in glucose is 40 by mass. What does that mean? That means 40 grams of carbon will be present in 100 grams of glucose. Yeah? Correct? Similarly, if I ask you the percentage of hydrogen in glucose, percentage of hydrogen in glucose, percentage of hydrogen in glucose, number 1, molar mass of glucose multiplied by, in 1 mole of glucose there are 12 moles of H divided by molar mass of compound multiplied by 100. Solve it, get the result. Right? Perfect. Similarly, molar mass percentage of oxygen in glucose by mass, 16 multiplied by 6 divided by 180 multiplied by 100. Done and dusted, right? Simple. So let's try to solve the equation based on the same fact. The first question. The question is the percentage of sulfur in insulin. The percentage of sulfur in insulin is 3.2 grams. What does that mean? That means in 100 grams of insulin, there are 3.2 grams of sulfur. Right? In 100 grams of insulin, there are 3.2 grams of sulfur. Calculate the minimum molar mass of insulin. Calculate the minimum molar mass of insulin. So the question is like this basically. We are given with the compound insulin. We are given with insulin. It's mentioned that the percentage of sulfur in insulin, it's mentioned that the percentage of sulfur in insulin is 3.2. That means sulfur is present in insulin. Sulfur is present in insulin. It's mentioned. Percentage of sulfur in insulin is 3.2. So let me write the same statement again. Percentage of sulfur in insulin, it is given to me as 3.2. Percentage of element in a compound is equal to molar mass of the element, molar mass of sulfur, multiplied by number of moles of element present in 1 mole compound. Now, do you know in 1 mole insulin how many moles of sulfur are there? I do not know that. I do not know how many moles of sulfur are present in 1 mole of insulin. Right? So how do I do that? How do I do it? This question then. Look at this particular statement. We are supposed to calculate the minimum molar mass of insulin. Now, you imagine when can be the molar mass of insulin minimum? If I assume that in 1 mole insulin, there is 1 mole sulfur. Right? The least moles of sulfur that can be present in 1 mole of insulin, that is 1. That is least. Right? Perfect. I have to calculate the least molar mass, minimum molar mass of insulin. Molar mass of insulin can be minimum only if I assume that 1 mole of insulin contains 1 mole sulfur divided by molar mass of compound. Do I write molar mass of compound or minimum molar mass of compound? And the compound here is insulin multiplied by 100. This value is equal to 3.2. Right? So one equation, one unknown. Calculate the minimum molar mass of insulin from here. And let me tell you, the answer will come out to be 1000 grams per mole. So this is the minimum molar mass of insulin which I was supposed to calculate. Quickly, you guys can let me know in the chats if it is super clear to you. Quickly, people. Everyone. Everyone in the chats. Quickly, let's finish off this chapter quickly. We have got just few more concepts to teach. Perfecto. Now, guys, one more thing I would want to make you understand. For example, I'm writing a statement like this. I'm writing Na2SO3 dot 7 times water. For example, Na2SO3 dot 7 times water. Till now, I was telling you how to calculate percentage of element in a compound. Now, if I ask you, tell me the percentage of water in the sample. Percentage of water in the sample by mass. What will be your answer? Till now, it was percentage of element in a compound. Now, I'm telling you here, calculate the percentage of water in the whole sample. So, what will be writing? It used to be percentage of element. Here, it's percentage of water. It used to be molar mass of element. Here, it's going to be molar mass of water. Multiplied by. It used to be number of moles of element in a compound. Now, it is going to be number of moles of water. Number of moles of water present in 1 mole of this sample. It is 7. Divided by. It used to be molar mass of compound. Now, this is molar mass of whole sample. So, molar mass of this part is 126 plus molar mass of this part is 18 into 7, right? 18 multiplied by 7 multiplied by 100. This will give you the percentage of water in this particular sample. Correct? For example, I'm writing like this. Let's say I'm writing like this. Na2SO3, Na2SO4 dot X times water. I'm asking you to write the equation for percentage of H2O by mass. Percentage of H2O by mass. It's going to be molar mass of water, 18 grams. In 1 mole of sample, how many moles of water are there? X divided by. Molar mass of this part is 142 plus molar mass of this part is 18x multiplied by 100. I mean, if you know how to write these equations, you can easily solve the questions based on percentage. For example, one simple question you have. I'm giving you one simple question. Na2SO3 dot X times water has 50% water by mass. That means percentage of water in the sample is equal to 50. It's given. Percentage of water in this sample will be equal to molar mass of water multiplied by 1 mole of sample contains X moles of water divided by molar mass of this part is 126 plus molar mass of this part is 18x multiplied by what? Multiplied by 100. This value is equal to 50. One equation, one unknown. Solve it, get the value of x. Isn't it simple? Can't you do this? Can't you do this, people? After solving, you'll be getting the value of x as 7. Right? Similarly, one more question. One more question of the same format. You can solve it on your own. One more question on the same format. Nothing different here. Nothing different. Nothing different, people. Clear? Clear to everyone? Yeah? Perfecto. Now, let's just move on to the last topic of the chapter. Let's just move on to the last topic of the chapter. And what is that? What is that? That is the easiest topic among all the topics of mole concept. And question frequently comes from this particular topic. What is that? Empirical and molecular formula. Okay. So first of all, how do we define the molecular formula? How do you define the molecular formula? It's simple, guys. molecular formula, it gives the actual ratio of atoms of different elements. Atoms of different elements in a molecule. In a molecule. What it means, you'll get the idea in some time. Okay? Empirical formula. Empirical formula. It gives the simplest whole number ratio. It gives the simplest whole number ratio between the atoms of different elements in a molecule. So one is molecular formula and another one is empirical formula. Let's try to understand and let's try to see what kind of questions can be asked from these two. Okay? Just to simplify it, just to make it clear to you. For example, I'm taking glucose into consideration. I'm taking glucose. Okay? Glucose. I'm writing its formula as C6H12O6. Right? Can I say this is basically, it is that formula of glucose which gives us the actual ratio of the atoms? So first of all, if I ask you, what is the ratio of the atoms here? It is 6:12:6. If I ask you, is it just the ratio of the atoms or it is the simplest ratio? You'll say it is not the simplest ratio. We can convert it in the simplest ratio. It is not the simplest ratio. We can convert it in simplest ratio. That formula, which gives you the actual ratio, which does not give the simplest ratio, which gives you the actual ratio of the atoms of different elements, you call that particular formula as the molecular formula. So this is the formula which is giving you the actual ratio of the atoms of different elements. So you'll be calling this as the molecular formula, right? Now, dear students, if I ask you to convert this ratio into simplest form, what you'll be doing? You'll be dividing throughout by 6. When you divide throughout by 6, 6 by 6 is 1, 12 by 6 is 2, and 6 by 6 is 1. Now I'm asking you the same question. Is this ratio the actual ratio or simplest whole number ratio? This ratio is the simplest whole number ratio, right? So as per this simplest whole number ratio, what should be the formula? It should be C1H2O1, correct? So can I say this particular formula, it is giving me the simplest whole number ratio of the atoms, and that formula which gives you the simplest whole number ratio of the atoms of different elements. What do you call that as? You call that as empirical formula. So this is empirical formula, this is molecular formula, right? Perfect. Now guys, few more things. With the help of molecular formula, what can we calculate? We calculate molecular mass. We calculate molecular mass with the help of what? With the help of molecular formula. Calculate the molecular mass of glucose. Use the molecular formula. 12 into 6 plus 1 into 12 plus 16 into 6. The value comes out to be 180 U. So this is the molecular formula. Molecular formula is always calculated with the help of, molecular mass is always calculated with the help of molecular formula. Similarly, there is a term called as empirical mass. There is a term called as empirical mass. Empirical mass, it is calculated with the help of what? It is calculated with the help of empirical formula. 12 into 1 plus 1 into 2 plus 16 into 1. The value comes out to be 30 U. So 30 U I'll be calling as empirical mass. One is molecular mass, one is empirical mass, right? Perfect till here? One is molecular mass, one is empirical mass. One more term I'm going to define. And what is that term? One more term, people, I'm going to define. And that term is basically N. What is N? N does not represent moles here. N is just a number. It is just a number like X, Y, Z, whatever. Okay, N is just a number. N gives me the ratio of molecular mass to that of empirical mass. N gives me the ratio of molecular mass to that of what? To that of empirical mass. There is one more result. What is that? Molecular formula is equal to empirical formula multiplied by n. Now you must be thinking, how come these results are true? Now have a look. If I talk about glucose, what is the n value for glucose? N value for glucose, molecular mass 180 U, empirical mass 30 U, the value comes out to be 6. This is the n value for glucose, right? Let's see whether this formula is valid or not. What is the molecular formula of glucose? It is C6H12O6. What is the empirical formula of glucose? It is C1H2O1. What is the n value for glucose? That's 6. So LHS, RHS, are they coming out to be equal? It seems. So this particular result is satisfied. Yeah? Okay? Perfect. I hope this is clear. And if this is clear, guys, one more thing that already I have mentioned, that molar mass is equal to 2 times the vapor density. Sometimes they won't give you in the question the molar mass. They'll give you the vapor density term. By using the vapor density, you'll be calculating the molar mass. Yeah? Now let's try to solve the questions which can be asked. Different types of questions which can be asked from empirical molecular formula. This is the simplest of all, okay? It is just you have to remember one general procedure. One general procedure you have to remember. For example, the question is, calculate the empirical formula of the compound that has this much percentage potassium, this much percentage chromium, and this much percentage oxygen by weight. So as per the question is concerned, Suresh Reddy, you can just drag the video a little back, it will be a replay for you. What is the point of repeating the same thing? Just drag the video a little back, it will be a replay. Yeah? Okay? Perfect. My dear students, there is a general way of calculating the empirical formula of a compound. How come exactly? How come exactly? Gautam, equivalent weight, I told you, I'm not going to teach you equivalent weight here. Equivalent weight will be done when I'll be teaching you concentration terms. And concentration terms, there will be a separate session, right, for concentration terms. Basically, when I'll be teaching you the solutions, in the solution chapter, I'll be teaching you this concentration terms. And there, all the concentration terms, molarity of dilution, molarity of mixing, of reacting, non-reacting, molarity of ions, molarity of ideal solutions, normality, equivalent mass, everything will be done and dusted. Okay. Look at the general procedure of calculating the empirical formula, guys. This is the simplest of all, okay? This is the simplest of all. As per the question, we have got a compound that contains 3 elements. Compound contains potassium, it contains chromium, and it contains oxygen. Okay? There is a compound which contains 3 elements. Now, as per the question is concerned, the mass percentage of potassium is given to us as 26.6. Chromium, it's given to us as 35.4. Oxygen, it's given to us as 38.1. What is this mass percentage? What does that mean? It means in 100 grams of compound, a compound is containing 3 elements, right? And in 100 grams of compound, you'll find 26.6 grams of potassium. In the same 100 grams of compound, you'll find 35.4 grams of chromium. In the same 100 grams of compound, you'll find 38.1 grams of what? 38.1 grams of oxygen. So basically, mass percentage, right? You can relate it directly with the mass. Yeah? It means 100 grams of compound contains these many grams of potassium, these many grams of chromium, these many grams of oxygen. Right? Do remember, the first step always to calculate the empirical formula, the first step is always to calculate number of moles. Number of moles, or you can call it as atomic ratio. You can call it as atomic ratio. Number of moles or atomic ratio. Given mass of potassium divided by molar mass of potassium. That gives you the number of moles of potassium. Similarly, given mass of chromium divided by molar mass of chromium. That gives you the number of moles of chromium. Similarly, number of moles of oxygen. So basically, let me just show you in the tabulated form. Have a look. This is the mass percentage that's given to us, correct? These are their respective atomic weights. The first step always to calculate number of moles, or you can call it directly as what? You can call it as the atomic ratio. This is the atomic ratio. Atomic ratio is nothing. It is just given mass percentage divided by atomic weight. Given mass percentage divided by atomic weight. 26.6 divided by 39, 0.68. 35.4 divided by 52, 0.68. 38.1 divided by 16, 2.38. It is giving you the atomic ratio. It is giving you the atomic ratio. You can call it as atomic ratio, or you can call it directly as number of moles. Okay? Now, dear students, this is the atomic ratio. Look at all these three terms. Which term has got the least value? 0.68. Divide all the terms by the least number. Divide all the terms by the least number. So 0.68 divided by 0.68, value is 1. 0.68 divided by 0.68, value is 1. 2.38 divided by 0.68, value is 3.5. Now, this is something which I call as least atomic ratio. This was atomic ratio. Now here I'll be calling this as least atomic ratio. Now, should I be calling this as least whole number atomic ratio? This is not the least whole number atomic ratio, because over here we have got 3.5. So convert it. So multiply throughout by 2. Multiply throughout by 2. This value is 2, this value is 2, and this value is 7. Now this 2 to 7, what is it? It is the least whole number atomic ratio. And that formula from which you get the least whole number atomic ratio, what do you call that formula as? Empirical formula. So empirical formula of the compound is going to be A2, Cr2, and O7. This is the empirical formula of the compound. That's it. Simple. Yes. Let me solve one more question so that you can understand it properly. Look at this question carefully, guys. In this particular question, we have to calculate the molecular formula of the compound. Okay, molecular formula of the compound. How do you calculate molecular formula? You know, molecular formula is nothing. It is empirical formula multiplied by n. So in order to calculate molecular formula, I have to calculate empirical formula as well as n. What is n? N is molecular mass divided by empirical mass. Do we know molecular mass of the compound? No. We just know vapor density of the compound. Vapor density multiplied by 2, 46 into 2 comes out to be 92. Molecular mass you got divided by empirical mass. I do not know yet. Empirical mass I do not know yet. Empirical mass I'll be calculating with the help of empirical formula. But right now I do not know the empirical formula. So calculate the empirical formula. A compound of nitrogen and oxygen. You have got a compound containing two elements, nitrogen and oxygen. Their mass ratio is given 7:16. Either mass percentage will be given or mass ratio will be given. You'll be following the same procedure, right? This is the mass ratio. Mass ratio will be given or mass percentage will be given, right? Now the first point is to calculate the atomic ratio. How to calculate atomic ratio? Given mass percentage divided by atomic weight of nitrogen. This will be 16 divided by atomic weight of oxygen. This value is 0.5. This value is 1. So this is atomic ratio. Now which one is the least term among the two? 0.5. So I'll be calculating the least atomic ratio now. So 0.5 divided by 0.5, the value is 1. Similarly, 1 divided by 0.5, the value is 2. So 1:2. This is the least atomic simplified ratio, right? So that's something which I'll be calling as empirical formula. So basically I got the empirical formula. It's going to be N1O2. It's going to be N1O2. So with the help of empirical formula, can't I calculate empirical mass, which is 14 into 1 plus 16 into 2. The value comes out to be again 46 only. This is the empirical mass. If you got the empirical mass, can't we calculate the value of n? N is equal to 92 divided by empirical mass, that's 46. The value comes out to be 2. So n we got. If n you got, can't you calculate the molecular formula, which is equal to empirical formula, N1O2 multiplied by n value is 2. So final result will be N2O4. So this is N2O4, which is basically the molecular formula of the compound. Isn't it simple and basic, guys? Isn't it simple and basic? Yeah? Isn't it simple and basic? Let me see if I have one more question so that I can give you that question as a homework. Right? Okay. You have to calculate empirical formula, okay? This is empirical formula here. this is your homework question. Perfect. So my dear students, I hope from now onwards, whatever question comes from the mole concept, you should be able to solve all the questions. Okay, and in the today's session, I gave you 4 questions on homework. I gave you 4 questions on homework as homework. I would want their answers in the comment section. And with this, your chapter 1 is over. Your chapter 1 is over, right? Now, one thing which I would want from you guys in the comment section, what is that? Let's kill chapter 2. Okay, and I'll let you know what is going to be our next chapter. That is the chapter 2 of your chemistry. This is something which I would want everyone to write in the comments. And this is my Telegram link, t.me/WASSIMSIRCHEM. This is my Telegram link. Perfect. Over here, I keep on telling you all the important things related to anything basically. Yeah. So do join it as soon as possible. Perfect. All right then, guys. So first chapter is done. Now let's hit the second chapter in the coming days. Till then, you take care. Bye-bye. God. See you all.